All right, in chapter 7, we're going to get into sampling distributions. Okay, so remember the idea that a distribution, you give us a way to display our data, whether it be a graph, whether it be a table, but we can see my outcome of my data. And we're going to talk about the sampling idea. And what we're going to do is we're going to take continued samples. We're going to take many, many samples and talk about what's going on here. So a couple terms we got to get straight first is, number one, if I'm talking about a parameter, I'm talking about something with my population. Okay? So I can talk about the mean income of a family in the state of Minnesota. I can talk about the proportion of students who pass the ACT test. Okay? So a lot of times though, we do not know what those values are. Okay? We do not know. It's hard to collect. So one of the things to keep in mind here is that what we talk about a lot of times is the parameter and population both start with P, they go together. So if I can calculate it, what I do is I take a sample, which again is a part of my population, and when I do that and I calculate something out, what I get is called a statistic, again, SMS. And what we want to do a lot of times is use that statistic to estimate that unknown parameter. Okay, so maybe what I do is I take a sample of a number of people in Minnesota, find their mean income, okay, and use that to estimate what the mean income is for the population of Minnesota. All right, so, but we're going to have variability every time I take a sample. Okay? Every sample is not going to yield the same thing. So for example, what I could do is if I take a class and I look at their test scores, and if I take a sample of 5 of them, okay, and if I find the mean for those 5 scores, if I randomly choose 5 students, I might get an 80%. The next 5 students, I might get a 74%. And it is possible for me at some point to randomly choose the 5 lowest scores. It is possible for me to choose the 5 highest scores. So we will have variability, okay? Those will change. Okay? So what we want to do though is we want to try and get the best estimate possible. So one of the ways we can go about doing is that take a large number of samples. Now, we need it to be from the same population. Okay. If I'm dealing with this test situation, I can't take a sample from a stats class and then a sample from an algebra class. Okay. 2 different populations. What we'll do then with my samples, we're going to calculate my statistic. Okay. Could be a mean, could be a proportion. And we'll find that statistic for each of these samples. Then what we're going to do is make a graph. A lot of times it'll be a dot plot of that statistic. So what I'm looking at and what I'm saying is that I'm going to take a random sample, number 1, find the mean test score, plot that on the dot plot. Take another random sample of 5, plot that mean. Okay, and continue for a while. And then what we want to do is look at, again, describing our distribution, the idea of shape, standard spread, and unusual, what's going on with our distribution. All right, so my sampling distribution, and as I said, this whole section is about sampling distributions. Of a statistic is a distribution of values taken by the statistic in all possible samples of the same size from the same population. So 3 things have to happen. Number 1, all possible samples. Okay, so I have to put together every possible group of 5 students and calculate that mean score. Okay. Number 2, all my samples have to be the same size. I can't have a sample of 5 and take a sample of 10. Okay, and then go back and take another sample of 5 and make a sample of 4. Third thing, again, we mentioned this already, needs to come from the same population. Okay, so whenever you hear the word sampling distribution, make sure those 3 things are talked about. Okay, if I have a sampling distribution, I'm taking all possible samples of what size from this population. Okay. Don't mix up sample distribution with sampling distribution. Sample distribution would be, okay, here's my 5 test scores. Okay. What's the distribution of my sample in that specific situation? Whereas sampling distribution again, all. Now, the other thing that's really going to start coming into play is dealing with our notation. Okay, very important that we use correct notation, so we gotta be careful with those. So, in this chart, we have our population and our sample situation. So my population, these are all gonna be parameters. Okay, so these are all gonna be parameters. If I talk about the mean, I'm talking about mu. Okay, you've seen that before, it's like a U. Okay, the population mean we'll talk about as mu. Okay. Standard deviation for my population, those two usually go together. Sigma again. And again, the zero with that little line above it. I'm talking about my sample though. Okay. Now we use X bar for my mean and S for my standard deviation. Now again, the difference between these is with standard deviation. If I have all my observations, I divide by n. If I don't, I divide by n minus 1. So my sample, I divide by n minus 1. That's your degrees of freedom. It allows a little extra variability for the observations we don't have. Okay. Then when we get into proportions, proportion again is a decimal value. Okay, so it might be stated in the problem as 35%, but we're going to change that to 0.35. So for my population, the parameter we talk about is P. Our sample, our statistic is P hat. Okay, P hat. Again, very important to use correct notation. Okay. All right, so the statistic that we calculate, we're going to say is unbiased if the mean of my sampling distribution. Okay, so once I've taken and put together this distribution of all possible samples of the same size from the same population. Once I find the mean of that sampling distribution, it's going to be equal to the mean of my population. Okay? It'll come into play a little more. You'll see it a little easier when we start actually getting into sample proportions and sample means. Okay? Now, here's the situation. If you look at the dot plot on the left, what that is your distribution of all heights for a group of students. So this is n equal 1, basically, as we can talk about. My sample size 1 has all my individuals. Now, here's my sampling distribution for the mean height for samples of size 4. Okay. Sampling distribution. Okay. We're talking about, again, all possible samples, size 4, from this population. It must be like a class. Okay. So, this observation right there obviously comes from finding the mean of the 4 shortest people. This observation up here is from the 4 tallest people. Okay, one of those should be. Okay. So that's what's going on. We're building that. And that's why there's so many more dots on the second one. But notice what's happening. And you can't really describe the first one very well. Okay, when we look at describing the first one, you know, you kind of maybe can see a little bit of symmetry, but you got so many gaps in there, it's hard to see. Whereas in the second one, what we do is now we eliminate those gaps. It's easier to see that we're symmetric and unimodal. We don't want to say normal because nowhere have we shown this one. Okay, so be careful with that. Let's talk about symmetric and unimodal first. And one of the things we'll talk about as a default answer for us. Anytime they ask, how can I improve my results? We always want to talk about increasing my sample size. If I were to increase my sample size, say to 10, what's going to happen is my variability is going to shrink. Okay, my curve is going to be less variable, so less spread out. You know, my peak might be higher, may not be higher, but that's what we would kind of expect. Okay. And so that's where they see this situation. Okay, they want to look at the sample proportions of people who watch Survivor. So the one in the green, what you're looking at is those are samples of size 100. Okay, and then on the right, in the red, those are samples of 1,000. Okay, so notice how your variability shrunk quite a bit by increasing your sample size. Now, your variability for your statistic is described by the spread of its sampling distribution. And spread is determined primarily by the size of my random sample. Larger samples give smaller spread. It does not depend on the size of your populations. as long as you have at least, your population at least 10 times larger. So a couple things here. Okay. Determined by the size of my sample. Okay. So variability is determined by the size. So when I look at it again, we talk about how the larger the sample, the smaller the spread. The size of the population doesn't matter. Okay. So for instance, one of the examples I use a lot of time is looking at some data from the state of California, state of Wyoming. If I take 2,000 as my random sample size, observations in California and 2,000 Wyoming, my variability should be similar. Okay. Because of the same size. It does not matter that California is larger than Wyoming by quite a bit. Now, this 10% thing, this could be a 10% condition. And what they do a lot of times, and eventually you'll see this, your sample is less than or equal to 1/10 your population. I think it's either say 10 times your sample, then don't deal fractions. It has to be smaller than your population. Okay? Now, we may not know the population sometimes. But say I'm looking at some information about residents of the state of Minnesota, and I take a sample of 100. Well, 10 times that 100 is 1,000. I know that's less than the population of Minnesota. All right, these targets on page 426, and they're a great thing to look at because they talk about bias and variability. Okay. Now, I always like to talk about this target. Your goal when you shoot darts is to get a bullseye. Okay, that's our goal. So what we look at, again, if we talk about situations, this is your best case.
Great.
All right, there may be a little jump here because I had to stop it, but we'll go over again. So we're looking at these targets, and again, whenever I shoot darts, I'm always trying to get the bullseye for the most part. Okay, so this obviously down here in letter D is our best case scenario. Okay, all my darts landed in the bullseye. Whereas this is my worst case scenario because I'm nowhere near the bullseye and my darts ended up all over, some of them not even on the board. Okay? So this is what we want down here in letter D. Okay? We don't have a lot of variability. Okay? My shots aren't spread out very far. Okay? Just like over here in A, yeah, I didn't hit the target, but you know, they're all in the same area. So that doesn't have a lot of variability. But now again, variability talks about spread. So since these are all spread out, that's what we're going to talk about, these as high variability. Now again, go back to your idea of bias. The mean of your sampling distribution is equal to the mean of your population mean. Okay? That's what's going on here. If I found, you know, the actual distance each of those is from the exact center, you calculated the average distance, taking into regard some positives and negatives, that would be really close to zero. Whereas this one, your middle of all of this is probably right about there, which is a long ways away from your true mean, or your true center. Okay, so that's why we have high bias. Now, your middle here, so think about where would be the middle, and again, you could deal with some formulas and things like that, but the middle of those is probably about there, which again, long ways away from the middle of the target, that's why we have high bias. With this one though, think about where it would, on average, it land. Again, I apologize, I have to take a break here, but your middle here isn't far away from the center, so that's why we have a little bias. Now, they'll show other situations with like a histogram or a bar graph sometimes where you'll have, there's your population parameter. Okay. This situation would look like this. Not a lot of variability, your middle is at the middle. In this situation, your middle is close to there, but they're going to be spread out. Okay. Here, you got a whole bunch, but you're nowhere near the parameter. Okay. And then here, you're spread out, and you're also not very close to your target. All right, so that finishes up that first section.